as a reminder, what we did sort of right at the end of the last class, we started to predict initially just the sign of the entropy change for the reaction, just using the number of moles of gas that are present. And that was pretty straightforward, right? If you determine the delta in gas, if the delta in gas is negative, you would expect a negative entropy change because the phase of the reactants and products definitely makes a difference for the overall entropy of the system. And so we did that with, right at the end, we did that with a chemical reaction that had an entropy change that was negative, and we were able to predict that from the fact that there were 2 moles of gas on the product side, 3 on the reactant side, leaving us with a -1, so a negative delta in gas. And then we calculated, so we predicted that it would have an entropy change of less than 0, and so we calculated that, and that entropy change turned out based on using the standard molar entropies, we did calculate an entropy change of less than 0, and that's -89 joules per Kelvin. But then we went to the situation where, well, you couldn't necessarily predict the entropy change for a reaction of, in this case, aluminum oxide reacting with hydrogen gas to form aluminum and water. And so we had to go to our table of standard molar entropies to do that. And so that technique was really similar to what you've done with the enthalpies of formation back in chapter 6. So that's kind of where we're headed with this next section, is the idea that, well, with free energy and chemical reactions, we're going to use those standard tables because we tend to compare reactions under the same conditions. And the same conditions for a general set of reactions that we might compare are going to be in their standard state. Right? And so just as a reminder, when you see something that has the little, there it is, that little knot up there, so delta H knot of reaction, right? That knot says it's under standard conditions. And just as a reminder, standard conditions, what they are. So standard temperature, and for chemical reactions, the standard temperature is a little bit different. I'm actually going to go to a table that we're going to look at in a second. We've seen already. Actually, if you look at the table here, right, this table has a set of standard conditions where it's the standard for that table is at 25 degrees Celsius. And so remember that chemical reactions, we're going to have a standard temperature that's 25 degrees Celsius, because the 0 degrees Celsius that we have for standard temperature in terms of gases doesn't work so well when you have an aqueous solution close to freezing to be good for us. So the standard temperature will be 25 degrees Celsius. We'll have a standard pressure, and that's going to be the same as it was for the gases. So that's, if you remember, is 1 atmosphere. And right, these are considered exact values when we say the standards here. The other one that we want to make sure is in our playbook is the standard concentration. And the standard concentration, this is for like an aqueous solution, for example, that's going to be 1 molar. So that's what we're talking about under all of these standard conditions. And that's something that'll come into play a little bit later in today's lecture when we start to compare reactions in their standard state to maybe not in their standard state. But if we do compare chemical reactions that are in their standard state, we can calculate the enthalpy of the reaction like we did back in chapter 6. We can calculate the entropy of a reaction like we did just in this last section. And also you can actually calculate the delta G in the same way, assuming your table gives you the delta Gs also. So you can calculate any of these 3 thermodynamic functions by subtracting the enthalpy, for example, the enthalpy of the reactants from the enthalpy of the products, or the entropy of the reactants from the entropy of the products, or the free energy of the reactants from the free energy of the products. And so to illustrate this, we're going to go through and we're going to do an example that has us do this. And then we're gonna see that, hey, if we aren't given, say, a free energy, standard free energy of reaction as data in our table, we can still calculate the standard free energy from those calculated energy of formations and standard molar entropies. So our example here that we're gonna go for with this particular topic is, as you can see, determine the enthalpy of reaction using standard enthalpies of formation. So we're going to do a little review of chapter 6. And the standard entropy of the standard change in entropy of the reaction using the standard molar entropies. And then we're going to use those values to determine at what temperature this following reaction will be spontaneous, or what set of temperatures, what range of temperatures it'll be spontaneous. So you can tell just by looking at this, right, that delta in gas is equal to -2. So from that information, you would think that, okay, well, if delta in gas is -2 because you've got 1 mole of N2 there, 3 moles of H2 on the reactant side, and only 2 moles of gas on the product side, you would expect, or you would predict, a delta S less than 0, so a negative delta S. But we're going to start here initially with our the enthalpy of the reaction. And so to do that, what we need is some data. And the data we need to begin with is the standard enthalpy of formation for each of these reactants and products. So the standard enthalpy of formation for, say, N2. Well, this is a substance that's already in its elemental state, its most stable state. So if hopefully you remember, the standard enthalpy of formation of an element in its most stable state is 0. And you'll actually be able to see that if we go to the table here. We go and find nitrogen. N2 gas has a delta H naught of 0 formation. Hydrogen's in the same boat. So we can say, well, the enthalpy change, or the delta H of formation, the enthalpy of formation for H2, that's also 0 because hydrogen gas in its standard state has an enthalpy of formation of 0. And so we really only have one of these that we need to deal with, and that is the enthalpy of formation, the standard enthalpy of formation of NH3 of ammonia. And so we can go to our table, just like we've done in the past, and we're going to find, okay, well, there's ammonia right there. So I'll underline that so we can get to that in the future as well. So negative 45.9 kilojoules per mole. And so if you look at this, you'll notice that, right, this is making 2 moles of ammonia for in this particular chemical reaction, which means this is 2 times. So the delta H of this reaction, okay, is going to equal 2 times the standard enthalpy of formation, so 2 moles of NH3 times that standard enthalpy of formation. Minus, well, the standard enthalpies of formation of both of the reactants are 0. And so we'll wind up with, very simply, a standard enthalpy of the reaction as written above as 2 times the standard enthalpy of formation. So negative 91.8 kilojoules. Okay. Okay, so that's what we've got for delta H of the reaction. Okay. We also can look at now the entropy of the reaction, and for that we need our standard molar entropies. And actually, we'll do that on the next page. I think that's probably going to be easier to just look at the values. And so remember, we've got N2, H2, and NH3. So we'll actually write that equation down at the top of the next page. So we've got N2 gas plus 3 H2 gas reacting to form 2 NH3. And so for this, we just want to go and look up our standard entropies, the standard molar entropies for each of these. So we can say that for N2. Right now, remember the standard molar entropies are values that are not going to be 0 for these substances, even though their standard enthalpies of formation are. And so we can go over to nitrogen right here, right? So if we look at nitrogen as this one there, the standard entropy, standard molar entropy of nitrogen is 191.6 joules per mole Kelvin. The standard molar entropy of hydrogen gas, right? We go over to toward the bottom, very bottom left corner here, 130.7 joules per mole Kelvin. And our standard molar entropy for ammonia is 192 joules per mole Kelvin right there. 192.8 joules per mole Kelvin. And we just use those. So we take our products, so 2 moles of NH3 times 192.8 joules per mole Kelvin minus 1 mole of nitrogen times 196 joules per mole Kelvin plus 3 moles of hydrogen times its standard molar entropy of 130.7 joules per mole Kelvin. And you do a little bit of math in here, you get 385.6 joules per Kelvin. The moles cancel out in each of these cases, minus 191.6 joules per Kelvin plus 391.8 joules per Kelvin. And so you wind up with a value of where you have your delta S of the reaction is going to equal negative 197.8 joules per Kelvin, okay? And so what we'll do is we'll take that value, we'll take the value that we calculated on the previous page for the, right, that's our delta H naught of the reaction. So we'll take that value and we'll use that to figure out our delta G. Excuse me, to figure out the temperature when delta G is 0. So we can say, okay, delta G naught of the reaction is going to equal the delta H naught of the reaction minus T delta S naught of the reaction. And that's going to equal 0 for the temperature that at which, right, the reaction changes from non-spontaneous to spontaneous. Okay, and so here we're going to say 0 will equal negative 91.8 kilojoules, okay, minus T times negative 197.8 joules per Kelvin. And so just something that you might want to do here is convert your kilojoules to joules or joules to kilojoules. Either way, just make sure you get that one set up. So here I'm going to simplify this. And so I'm going to say negative 91.8 times 10 to the third joules plus T times 197.8 joules per Kelvin. I just got rid of my negative signs by multiplying them together. And so you can find T will equal 91.8 times 10 to the third joules per Kelvin divided by 197.8. Oh, I got my units backwards here. It should just be joules divided by 197.8 joules per Kelvin. Okay. And so when you do that, you plug this in and you get a value of 464.1 Kelvin. Okay. And so there's our temperature. That's an important temperature for us. But the question asked, if we go sort of review the question now, at what temperatures will this reaction be spontaneous? So we can come back down here and say, okay, well, based on the equation up here, right, the minus T delta S, we want our temperatures to be small because our delta H, right, delta H is negative and so is delta S, right? So we want the temperature to be low. So at temperatures below 464.1 Kelvin, the reaction will be spontaneous. Okay, and that would be how you'd phrase that. Now using basically some reminder of some skills from chapter 6 back in Chem 101 and stuff that we just learned. Now keep in mind that had I asked you to just calculate those temperatures, you could have gone or if I just asked you to calculate the delta G naught of the reaction, you could have gone and just calculated delta G naught of the reaction based on the values that you see in here, right, from this table on the left. Okay, so hopefully that's pretty straightforward. A little bit of review, something you've done before. It's not too hard. You'd look up tables, you do a little math, and you're good to go. And so that brings us to sort of a bit of a culmination of a lot of this stuff, and a relation to stuff that we have done in the past this term. Okay, so I put these two sections together. Section 17.7 is pretty short. Basically, it reintroduces that reaction quotient, right, Q. If you remember that from equilibrium. And we're gonna bring that back into play here. So this is basically all about free energy and the direction a chemical reaction will proceed. Because remember, when we calculate the delta G naught, right, delta G naught is something we can calculate from that table of standard enthalpies, but that's different, right, from a delta G, okay? So you can say, well, delta G of a system or reaction will only equal delta G naught of that system under standard conditions. Now, that's all great if you have a reaction under standard conditions. Remember, you're saying that all of your concentrations are either 1 molar or your pressures are 1 atmosphere and your temperature is 25 degrees. But that's the difference between a delta G and a delta G system. Delta G can occur under any conditions, any concentrations and temperatures. And so what we need is, in order to predict whether a reaction will be spontaneous, we need to know the delta G for the system that's actually given to us, not just for the standard system. We should be able to predict it for all kinds of other systems. And what we do know is that if we have the enthalpy, or excuse me, the free energy of a reaction is calculated. Remember, this is not a delta G naught. This is not under standard conditions. If the reaction has a delta G that's less than 0, it's going to be spontaneous in the forward direction. If the reaction is at equilibrium, we'll have a delta G that's at 0. And if the reaction is going in reverse, the delta G will be greater than 0. And so this is something we can actually relate to things that we've done in the past. One of those things is going to be the reaction quotient and its relationship to the equilibrium constant. And that, in our next slide, is where we start to see how these things are all related. So as a reminder, well, first off, that the stuff that we just looked at on the slide a second ago is this idea, these two columns here. This stuff here is what we were just talking about. We're going to relate that now to what we've done in the past. So when we compared Q versus K, okay, if Q was less than K, we said it was going to go in the forward direction. Okay, so the relationship there says, okay, well, Q over K, if Q is less than K, then the ratio of Q over K will be less than 1. And so if you take the log of something that's less than 1, that will also have a value, or that will have a value that's less than 0. And so these two things are kind of tied together, right? The natural log of that ratio of Q over K, or the reaction quotient divided by the equilibrium constant. And so those things we're gonna find, they translate very well together, right? If Q and K are equal, right? So if Q and K are equal, that means we have a Q over K that equals 1, and the natural log of 1 is 0. Well, for an equilibrium, the delta G is equal to 0. So those things are going to translate. And of course, if Q is greater than K, then you're going to have a value for Q over K greater than 1, and the natural log of Q over K will be greater than 0. So you'll have a positive value for delta G, which means the reaction will go spontaneously to the left, or in reverse. And so we're starting to see now, we can look at these chemical reactions from the standpoint of equilibria, but we can also look at them from the standpoint of thermodynamics as a way of predicting whether a chemical reaction will proceed in the forward direction, remain at equilibrium, or move to the left, in the reverse direction. And so how are those specifically related, right? Because this is just telling you something about the sign of these values. Well, it turns out the free energy of a reaction, this is an important equation here. The free energy of a reaction is going to equal RT times the natural log of K. Something that's been experimentally determined, where RT is, that's the temperature in Kelvin, and the ideal gas constant. Of course, this R is in terms of energy, right? So this R here that we're looking at is the 8.31 joules per mole Kelvin, right? It's in terms of energy. We're dealing with free energy, right? The temperature is in Kelvin. And so those are just a proportionality constant for this. And if you do a little bit of the log math, use your log rules, you can split this up so you get the delta G of the reaction is equal to RT ln of Q minus RT ln of K, right? That's just the log rules. So if we think about a reaction now in the standard state, okay, if you think about a reaction in the standard state, remember, 1 atmosphere, and this is what I was alluding to earlier, 1 molar, okay? If we have all of our concentrations are in 1 molar, well, remember the value that we have in the Q, right? The value for Q will be 1, because remember, it's if all of the values of all the concentrations and all of the pressures are 1, right? Then your Q becomes 1 because you're dividing 1 by 1, right? 1, whether it's squared or cubed, doesn't really matter for the the reaction quotient. They're all 1 values. Remember, the values that we have in the Q are standard divided by their standard value. So if you take a 1 molar, divide it by its standard value of 1 molar, you get 1. So essentially Q becomes 1 when you consider this to be a reaction in its standard state. But the other thing is, if we're talking about the free energy of a reaction in its standard state, well, then we can put this little naught above the delta G, right? Delta G of the reaction now becomes delta G naught of the reaction. And so we have these two things that come out of this consideration, right? If we're looking at stuff in the standard state, right, delta G becomes delta G naught and Q is equal to 1. Well, if Q is equal to 1, well, the natural log of 1 is equal to 0, so that goes away, which means that our standard state free energy change for the reaction is going to equal negative RT ln of K. And so that right there is going to tell us our free energy change for the reaction. If you have substances in their standard state, it's going to be related to the equilibrium constant, okay? And so we can then take and plug this value in. If we go just back to any old delta G, right, we take this and plug it back into the original reaction, right, what this becomes now is the free energy change of any reaction will be the free energy change of the reaction in its standard state plus this RT times the natural log of Q, where Q is the concentrations of the products and reactants in whatever state they happen to be in, not necessarily the standard state, okay? And so this right here now allows us to predict, just based on, say, the table we had above, before, where we looked at and could calculate the free energy change of a reaction. And now we can look at it from the standpoint of, well, we can calculate that part, and then we can calculate the this RT ln of Q, assuming we know the temperature and the concentrations of the reactants and products. And that's what our next example is going to do. So we're going to consider a reaction, in this case, N2 plus 3F2, right? So nitrogen gas and fluorine gas react to form nitrogen trifluoride, and this happens at 800 K. So the equilibrium mixture has the partial pressures listed here. And so here the partial pressure of nitrogen is 0.021 atmospheres. The partial pressure of fluorine is 0.063 atmospheres. The partial pressure of NF3 is 0.48 atmospheres. And so we can calculate the delta G of a reaction at 800 K. Okay. Actually, something's off here. This should just say a mixture. This should just say a mixture. So I'm going to scratch that out right there. And I'll scratch it out more in a bit. So there's a typo in there. And so what we can do here is we can understand that the delta G of this reaction will equal delta G naught of formation minus RT ln of Q. Okay, where Q is going to equal, well, this is just coming from our concentrations above, right? 0.48 for the partial pressure of NF3 squared over 0.021 times 0.063 that comes from our reaction quotient expression. And so to do this particular calculation, this is a pretty simple one. What we can do here is, and the reason I give you the delta G of formation here, right, is because you can figure out the delta G, this shouldn't be the delta G naught of formation, this should just be delta G naught of the reaction. So what you should have here is the delta G naught of the reaction, I'm getting ahead of myself on here, should equal 2 moles of NF3 times the standard free energy of formation. I guess this should be labeled as NF3, but that's the only thing that has a value of those because this is a formation reaction. It just happens to be a double of the formation reaction. So 2 times negative 181 kilojoules per mole minus 0 will give you the delta G of the reaction of negative 362 kilojoules. Okay, and so we can just plug those values in. Delta G of the reaction will equal negative 362 kilojoules plus, that should be a plus RT ln a Q. Well, R is 0. No, that's not right. 8.31 joules. Come on. Make this clearer. There we go. So this will be 8.31 joules per mole Kelvin times the temperature, 800 Kelvin, times RT, times RT, times the natural log of Q. 0.48 squared over 0.021 times 0.063. Okay. And so if you do the, if you calculate this.
Is the 0.063 cubed?
Oh, yes, excuse me, it is, totally is. Ah, oops. Yes, it is. Aha. All right, thank you. So, here we go. So we've got now basically a simple calculation to do, right? We can calculate our Q. Right, so our Q should be 4.4 times 10 to the 4th, right? And so we can plug that value in there. So negative 362 kilojoules plus 8.31 joules per mole Kelvin, 800 Kelvin times the natural log of 4.4 times 10 to the 4th. So you should have, my math is right. I'm checking on this here for a second just to make sure I didn't mess something up earlier. Yeah, okay, good. So what we have here, and that is going to be negative 362 kilojoules plus 7.1 times 10 to the 4th. This is going to be in joules, okay, or negative 362 times 10 to the 3rd kilojoules, right, plus 7.1 times 10 to the 4th. So should come out to negative 291 2.91 times 10 to the 5th joules, or, oh, that should be negative, or negative 291 kilojoules. Okay. So I'm going to move this back up where I got a little bit more space. So we can say our delta G of the reaction is equal to negative 291 kilojoules. Okay. And that's basically now just a way of comparing the free energy of a reaction to the free energy of the reaction when it's in its standard state. So it's basically going to tell you now, well, a negative value for delta G says this reaction is going to be going in the forward direction. And so it'll be spontaneous in the forward direction, okay? Oh, there's our standard table. And that really takes us to the end of chapter 17 material.